Okay, so we have introduced the gradient descent algorithm. Then next I'd like to introduce several other gradient descent variant algorithms, the momental, the adaptive gradients, as well as atom algorithms for you. So before we introduce them, I'd like to provide a revisit about this gradient descent algorithm for you again. So according to the gradient descent, we are updating these variables iteratively in each step, right? And we calculate the current gradient, and also based on the current variable values, we can update it, right? So actually, if we check this updating process, it would be very similar as if we are rolling a stone down from a hill, right? Let's assume if we are throwing a stone from the hill downward, actually the stone will roll down, right, gradually and iteratively. And the way we are doing updating the variables is very similar to rolling a ball from a hill. And the starting point is the location we throw the ball, right? And if we're rolling down the hill, and if this ball stops finally, then the ball will achieve the local minimum for the function, right? And if we check this equation for the updating again, we are updating this theta according to this formula, right? We have theta I plus 1 equals to theta minus alpha times gi. If we compare this updating process as if we are rolling a ball, actually we can also provide the physical meaning or physical interpretation for each of the terms here, right? Like the theta actually denotes the location of the ball, right, at each of the step. Like theta I denoting one location of the ball, right, at a certain time. And how about this gi? This gi equals to what? Does this gi equals to the current speed or not? Right? Does this gi equals to current speed or not? Actually not, right? This gi equals to what? It equals to current acceleration, right, of the ball, actually. Because we are calculating the partial derivative of this loss function regarding to the variable at some locations, right? It denoting the trend for the function. It corresponds to the acceleration, right, of this ball at a certain location, right? It's not the velocity, it's not the speed of the ball, actually. Then how about this alpha? This alpha is more like a time gap, right, or the unit time for the ball to move forward. If this alpha is a very large number, it denotes a very large time gap or time unit. It allows this ball to move more time. It will be a larger step, right? If this alpha is very small, it denotes more like a very small time unit or time gap. And now this ball to move, right? So we are updating the variable according to this formula. This formula is somewhat very weird, right? Because we are updating this variable, this location, according to the acceleration. And also we use 1 alpha for all the variables. Because for deep learning model, we have so many variables, and this gi will be vector. So will be the theta I, right? And theta I plus 1. They will all be vectors for all the variables. Then we have to question in our mind, right? Why we are updating the location of the variable according to the acceleration instead of the speed or the velocity? Why not use the speed for us to updating these variables? Also, why we have to use one single learning rate for all the variables? Can we assign different learning rates for different variables? Because different variables will have different gradients, right, in their directions. These are the two main questions in our mind, and they are also the main motivation to propose new algorithms to improve this gradient descent updating equation as shown here. Okay, so the first variant algorithm I'd like to introduce is called the gradient descent with momentum. This momentum is more like the speed for the ball to move in the learning process. And we do some minor modifications to the updating equation we showed before. And let's assume we still have the loss function, and we are still calculating its partial derivative to the variable based on the current location. Let's assume we are assigning a partial derivative at its current location to be gi. It represents the current acceleration, right, as we mentioned before, if we provide the physical interpretation of this updating process as a rolling ball of the hair, right? This GI is more like the current acceleration. And for the gradient descent with momentum, this algorithm, it introduces a new variable to represent this momentum or to represent this speed of the current location. So we can represent a new variable as VI or VI plus 1, right? So this VI can be updated. It denotes the current momentum, something like a velocity or the speed of the current ball, right, at the current location. And we will also update this VI with this formula as shown here. It equals to the gamma times VI plus alpha times GI. So this VI denoting the speed at the previous location. We have a memory for the previous location, right? And according to the previous location as well as the current acceleration, we can decide the current momentum or the current speed, right, for updating the variables. You can follow me, right? So we introduce a new variable to memorize or to remember the speed for the locations of the ball. This speed of the ball, it is decided by both the previous speed as well as the current acceleration of the ball, right? So by combining them together, then we can decide the current momentum or the current speed of the ball, right? You can follow me, right? Okay, so this alpha is the learning rate, and this gamma denoting another hyperparameter. We have to assign them, and it denoting the momentum term weight. Normally we can set this one as 0.9 in our this algorithm by default, but you can also tune it by yourself if you have a better value to be assigned for this gamma. Okay, so with this speed, then we can update the location, right, of the ball or the value for the variable. We update according to the formula by the theta I plus 1 equals to theta I minus the speed. You can follow me, right? So in this way, we can update the locations of the ball according to the speed, right? It will makes more sense than the previous equation because we are updating the location according to acceleration. It will be somewhat weird, right? And here we are updating according to the momentum, like the speed of the ball, right? And then we can decide the new locations. Then you may wonder what will be the advantages for this kind of momentum compared with no momentum, compared with vanilla gradient descent. And on the right side, we also show you with a plot. Generally, if we have the momentum, it allows us to update the variables with a much faster way, right? In a much faster way because we know the speed of the ball. And it will also create some potential problems sometimes. Let's assume we are rolling a ball or we are updating this variable from this point. This is the initialization of the point or the location from where we throw the ball, right, off the hill. Initially, because we don't have speed for the ball in the very beginning, and the initial changes of the location only rely on the gradient, right? So the updating for the variable maybe is very minor in the very beginning. However, as this ball rolls down, it will have some speed, right? As well as the current acceleration, so the ball will move very fast, right? In the following steps, the gap will be larger, right? We are moving the ball in a fast manner by considering its speed or the momentum. Since this ball moves very fast, if we reach a point very close to the global minimum or the minimum, then the ball will still have very fast speed, right? It will move overhead, maybe to the right hand side, right? And then the ball recognizes, its current gradient will be a positive number. However, its speed is still to go to the right hand side. And this ball will do a very sharp stopping, right? And then move to the left hand side until it will come back to the minimum. So by considering this momentum, it allows us to update this variable in a very fast manner. However, when we are doing the conversion steps, it will cause some potential problems because we will have extra steps until we can achieve the convergence, right? Because we can potentially go overhead because we have a memory about the speed. And this gradient will do the sharp stop for speed and then reverse direction and go back until we do the convergence, right? Okay, so this is the way we can change the gradient descent algorithm by considering the speed for updating the variables. Then we can move to the second question. Can we have different learning rates for different variables instead of using one single learning rate for all the variables, right? And to achieve this target, we have to introduce another algorithm. It's called adaptive gradient descent, or the Adagrad. So the Adagrad actually considers to assign different variables with different learning rates. And the way to achieve this is by memorizing the historical gradients of the variables. Here I need to mention, because for this algorithm, we don't consider the momental term. In other words, we are still doing updating based on the vanilla gradient descent. However, to some changes to allow we have different learning rates for different variables. And the way we do this is to memorize the gradient or the historical gradients of different variables. Here, in this system, we are still calculating the partial derivative of the loss function regarding the variables and iteratively. And here we have two indexes. The first is I. I denotes the iteration. The I is iteration. We do the updating, right? And we also have J. J denoting the J's variable. Because we have so many different variables, and we assume this GI will be a vector covering all the variables, right? And depending on the partial derivative of loss function regarding a certain variable as well as the current variable values, we can decide or we can calculate its current gradient, right? It's like an acceleration term, right, for the variable. Then we do some minor changes to the updating equation. We're updating this J's variable for the next iteration, I plus 1's iteration for J's variable, according to this formula. This part is very trivial, right? And we are updating this according to the previous variable value, and we minus some terms, right? And we minus the term which is decided by both the learning rate as well as the gradient, right? It's kind of gradient. Then the main changes here is we add some terms to modify the learning rates from alpha to alpha over the square root of a summation for all the historical gradient of the variable in history plus the epsilon. And how can we understand this term? So let's assume if we have some variables with very small gradients in the history. And for such kinds of variables, because this gradient is so small, in other words, we will update them very slowly because the gradient is so small, right? For small gradients, we are moving very slow actually. And we may wonder if we can speed up slightly for these kinds of variables with very small gradients. The way is we do here is to divide this alpha by its gradients. If the gradient is so small and we further divide them, then we can enlarge the learning rates, right? We can enlarge the learning rates for such gradient, for such variables. So for the variables with small gradients, then we can enlarge the learning rates for them by dividing this alpha with the historical gradients, right? On the other hand, for the variables with very large gradients, then this updating step will be very large, right? We may consider to slow them down because if we are moving them very fast, it is high likely we can do them in a zigzag way, right? And cannot achieve convergence. Then the way we do is also dividing this alpha by them. For the variables with large gradients, by dividing the historical gradients, then we can slow down or have a small learning rate for them instead, right? So the summation here actually memorizes historical gradients. For the ones with small gradients, we can, by dividing them with the historical gradients, then we can enlarge the learning rates. However, for the ones with large gradients, then we can lower down the learning rates instead. In this way, we can balance among all the variables and allow them to have different learning rates depending on their historical gradient records, right? And you may also wonder why we have this epsilon here. This epsilon is a very minor value. It is added here because sometimes we may have the summation of the gradients to be 0. And if so, then this division will make no sense, right? So we add one epsilon here to avoid this summation to be 0, to ensure this equation can hold and has a physical meanings. I hope you can follow me for the adaptive gradient descent and how we use this algorithm to allow different variables have different learning rates. Okay, this is where we address the second question. We can have different learning rates for different variables. And you may also wonder, can we combine them together? After someone has done this already, we can combine momentum with adaptive gradient descent together. It allows us to consider both the speed of the variables to be updated as well as different learning rates for different variables. The algorithm we introduce here is called ADAM. It denotes this adaptive momentum estimation. Okay, so let's have a look at how this ADAM works. This ADAM also considers this gradient, right, for the variables at a current location. This is more like acceleration we introduced before, right? And this ADAM introduces two variables. The first variable is called mi. Mi is more like the momentum term or the speed term we introduced before, right? And this speed or the momentum is decided by both the previous speed as well as the current acceleration we calculate here, right? And we sum them together controlled by one parameter, beta 1. This beta 1 will be a hyperparameter, right? This beta 1 is one hyperparameter. We have to assign them manually. And in this way, we can decide the current speed for the variables to be updated, right? And for the ADAM algorithm, it will further introduce another term here. And this term is for memorizing the historical gradients. It is used for memorizing the historical gradients. And I will denote this term as the VI. So VI equals to the VI minus 1 plus the current gradient square. So, and it is also controlled by another hyperparameter, beta 2. We have also to assign this beta 2 manually with some values for this algorithm. Another interesting part for this algorithm, it introduces another step for the bias correction. So, we have tested this algorithm. If we do not consider this bias correction, then this algorithm will not work very well or will work very slowly. If we have the bias correction, it allows this algorithm to work very fast and also effectively. The way we do the bias correction is to normalize this mi and vi, these two terms, according to their parameters as well as iterations. So we will normalize this term by dividing the mi to a term. The term is denoted by 1 minus beta 1 raised to I. This I denotes the index of the iterations, and we use this I as a power. Similarly, we can also normalize this vi vector with this parameter beta 2 as well in a similar way. Okay, and you may also wonder how we do the initialization of mi and vi. We can initialize them, both them to be 0 vectors, and beta 1, beta 2 are usually close to 1 actually. As we have both the speed as well as the history as well as the record of the historical gradients, then we can write down the updating equation for the variables. And the updating equation is denoted by the theta I plus 1 equals to theta minus alpha divided by the square root of vi, and then times mi. Remember, we mentioned this mi denoting the speed, right? It is very similar to the momentum term here. We update according to the speed. And as to this vi, it is more like the summation of all the historical gradients of the variables, right? It is more like the term we use in the Adagrad, this algorithm, right? Then in this way, we can allow different variables to have different learning rates, and we also consider the speed, right, by incorporating this momentum term into the updating equation. And this epsilon is added here for avoiding this term to be 0. In this way, we can also ensure this equation will hold, right? And this will not be 0 actually. Alright, so this is the Adam algorithm we can use for updating these variables. And you can see it is more like combination of the momentum as well as this Adagrad, right? These two algorithms together. We define the momentum term for memorizing the speed, and also defines the VI term for memorizing the sum of historical gradients. It will be used for adjusting the learning rates for different variables. Okay, so in applications, normally this algorithm will be more robust and also much more faster in many cases. It also depends on your application problem, your model, and other factors. You have to decide your optimizer by yourself. Alright, so in this page, you also provide you with a comparison among different optimizers. We compare with the vanilla, SGD with momentum, adaptive gradient descent, IMS prop, as well as Adam. We didn't mention the IMS prop here in lecture. It is also a variant of the gradient descent. So according to the performance by different optimizers, we can see that they are starting from the same point. However, the Adam as well as the IMS prop can achieve convergence much faster, right? Because they are moving faster than the remaining algorithms. And if we also compare this SGD with momentum, actually, this SGD with momentum will move faster, right? Because we memorize the speed. As to the Adagrad, it moves very slow because we only assign different learning rates for different variables. We do not have any momentum terms for them, right? The speed will be very comparable to SGD actually for this example. As to the optimizer to be used for your real application or in your project, actually the above slides, they are all the pure theoretical analysis about the optimizers, right? We have no guarantee which optimizer will outperform other optimizers in the real applications. You may need to try different optimizers in your project and also choose the best one for your algorithm. As to the learning rate tuning, if we have a small learning rate, then it will need to very small convergence, but it will converge to the local optimal, and larger learning rates will move faster but may keep jumping without convergence, right? Sometimes it can even jump out to better or worse local optimals, depending on the function we are defining as well as on your problem, right? So when you are doing the applications, to choose which optimizer to use, you can try different ones. Okay, so that's it for this part on the gradient descent variance. And next we'll move to the last part on the outputs as well as loss function definition.